So we're going to continue from where we left off, which we're looking at vector cross products. And my goal today is to continue with these guys and show you some other interesting properties of them. I'm going to show you how you can use cross products to find the area of a parallelogram or a triangle that's generated by two vectors in 3D. Going to find the volume of an object called a parallelepiped, for instance. And we're also going to use cross products to test if three vectors are coplanar. And what does that mean when you say they're coplanar? So that's our first goal for today. So, and then after that, we'll do an intro to equations of lines and planes in three-dimensional space. Right. I think I'll change my letters. I'm going to call my first vector A and my second vector B, just so we don't get hung up on there we go. Here are two vectors, A and B. If you want to find their cross product, the best way to set it, to do it, is to set up this three-dimensional vector and find its determinant. So you start with ijk, and then you do vector A and its components go in the second row, and then you do vector B and its components go on the third row. It's pretty easy to set up. And then it's going to be so many I, take away so many j, that negative's important, and finally add so many k. And then you basically go through this, it's like a cover-up technique, I guess. If you want to know the vector I, you cover up column I. And then you go major diagonal, subtract minor. In this case, the major diagonal is 3. 3 take away 4 gets you -1. If you want the j component, major diagonal -9, take away 8, looks like that's -17. And the last one, 3 times 2 is 6, take away -4 is like adding it, 6 add 4, I believe gets you 10. And then what do we have? We have -1, 2 negatives make a positive, and finally 10. That's quite mechanical, really, isn't it? As long as you know the numbers for A and B, you can basically do any two cross products in the universe. I mean, if the numbers are weird or awkward, I guess you use the calculator, but that's about it. We feel comfortable about just a generic find a cross product for of two vectors. Go that good? Now suppose we have two vectors. Let's call them U and V this time. And we get their cross product. And it ends up being the zero vector. And U and V were not the zero vector. What's the conclusion about the U and V? What can we state for sure that their connection is? They're not just two random vectors that have nothing to do with each other. They are not orthogonal. I know exactly, or I think I know exactly what you're thinking about.
Mr. Robertson. They must be coplanar, meaning that they are on the same plane.
Even more than that, but that is coming up. You're right, coplanar is a term. U and V are parallel. Now, coplanar doesn't necessarily mean parallel, right? In fact, two vectors are always coplanar by the definition of coplanar. Three vectors are coplanar is the usual way that you talk about coplanar. To give an example, if you have 2 points in three-dimensional space, right, and you join them together, those 2 points are collinear. That's a different word. They're on the same straight line, but of course they have to be. They're only 2 points. Don't you need 3 points to be collinear? You know, for a property of collinear to really make sense, don't you need 3 points? And they are all on the same straight line. We call that collinear. I haven't talked about coplanar, and we will, but I'm going to hold back on that because there's some other things we're going to do before we hit that. Now, the person who said that they are orthogonal, there's a property that is very similar looking to the one we just did, but it doesn't involve the cross product. If the dot product is 0, then U and V are orthogonal. But when the cross product, that looks like an addition there, but it's a cross. When the cross product is a 0 vector, then U and V are parallel. So you notice that these two may look similar, but the conclusions about what are the connections are different. In fact, you could use that as a test. I have 2 vectors. Are they parallel to each other? Well, just find their cross product. If it's a 0 vector, you can then say, yep, these 2 vectors are parallel. Now, parallel means, what I mean by parallel is they look like that, right, in the 3D world. There is other versions of parallel. See if the vector u is a scalar multiple of the vector v, doesn't that also make them parallel to each other? They're going in the same direction, just one of them's longer than the other, or shorter, depending on your perspective. So, now, let's go back to A's and B's. Suppose I have a vector in 3D space that looks like this. And I get another vector in 3D space that looks like this. You can build a parallelogram. Looks like that. So far, so good. Now, if you want to find the area of the parallelogram, and we talked about this very quickly at the end of the last lesson. If you want to find the area of the parallelogram, this one here, at least, it's equal to the magnitude of the cross product. So if we had these 2 vectors over here, A and B, and let's pretend they were these components, then if I wanted to find the area of this parallelogram generated by A and B, all I would need to do would be to find the magnitude of this vector here. So it would be equal to the square root of 1 squared, well, technically, -1 squared, plus 17 squared, plus 10 squared, which is the square root of 1. I'm not even going to try and do 17 squared this time in the morning. 289 plus 100. That's 290, 390, square root of 390. Now, if this was a question in WebAssign, for instance, that would be an acceptable answer, I'm pretty sure. I've had to check some of these ones. Of course, sometimes you can simplify these things. This is 3 times 130, which means 4 works. So let me check that one out. 390 divided by 4 gets me, no, it doesn't work. I take it back.
Mr. Robertson, why is the area of the parallelogram the magnitude of the dot of the cross product and not the dot product? Why is the
Well,
area?
the magnitude of the dot product of these two guys,
You mean cross product?
right, well, depends on how we're comparing them. I think your question said, why is it not the magnitude of the dot product? It's one of
Yeah.
those that we do not go into the depth of where these things come from. It's a bit like, why is the cross product equal to this weird thing? There are good mathematical reasons for it, but they're beyond the scope of this course. If you do 250, which are vector, what's it called? Linear algebra, you'll touch on it a little bit. There's things called vector spaces. And from vector spaces, you can generate quite a lot of very interesting results. This particular one came from that branch of mathematics. In our world, we just have to say, okay, I'll trust you that that's how you get a cross product, and I'll trust you that this magnitude is that guy. Anyway, I was not a very satisfying answer, I know, but the analogy. Can you imagine that you were 11 or 12 or whatever age that you started doing algebra, and you wanted to know the answer to some of the algebra questions, like why is this true or why is that true? And we say to you, look, you don't need to worry about that yet. But eventually, you know, you get to some place maybe in calculus where we prove it to you, or, you know, maybe in Math 141, you see a proof of it. You know, why is the coordinates of the vertex on a quadratic x equals negative b over 2a? You know, why is that true? Well, in 141, you probably were just told it, but in Calculus 1, we can actually prove it. So these things are all provable, but we're not going to prove them. That's as best as you're getting from me. Right, I'm going to call that the right answer. I can't think of anything off the top of my head. What wouldn't be a good idea would be what I'm about to write down right now. We do not like decimal approximations unless the question itself specifically says, give the area of the parallelogram to two decimal places, in which case that is totally justifiable. Now, if the area of the parallelogram is the magnitude of its cross product, then closely connected to that is the area of a triangle. And what we mean by that is, if you join here to here, and you use A and B as two sides, you see you generate a triangle. And the area of the triangle is half the area of the parallelogram, which means that it's half of that, which means it's half of that. So if I've got two vectors, A and B, or U and V, or whatever letters they decide to choose, I can find the area of the parallelogram that's generated by them. It's this fella. I can find the area of the triangle that's generated by them, just this fella. And I think there's a homework question that asks you to do that. Pretty sure there is. Any more questions? Are we good?
I have a question clarifying the IJK formula.
Yes?
So for dot product, it's I plus J plus K, but when it's cross product, it's minus J plus K.
Yeah. Annoying, isn't it? They're not consistent. There is reasons for that. If you go into 3x3 matrices and you want to find the determinant of a 3x3 matrix, you'll find that this negative is also there. It's the peculiarities of the process. In a kind of way, it's magic. And when I say magic in math, I mean, you just have to trust that it's true, that it works. It would be much nicer if things were like the same kind of thing. And when you do a dot product, there isn't any I, J's, and K's anyway, technically. There's only one number plus a second number plus a third number. So the I, J's, and K's have actually disappeared. we good? I'm moving on if I get any regression now. So right now, if I give you two vectors, you should be able to find the cross product. If the cross product is 0, you know that means they're parallel. If you use those two vectors to form a parallelogram, you now know how to get its area. It's the magnitude of the cross product. And if you want to find the area of the triangle, it's half the magnitude of the cross product. And every single one of those things I guess I said are, trust me, I'm a mathematician. That's essentially, you're trusting that the cross product formula works and that the magnitudes that we give you do in fact equal the things we say they are. Now, we're going to look at a thing called the parallelepiped. Parallelepiped. Yes, I think that's pretty close to it. I can't spell. Could be parallelepiped. How's that look? Both look wrong. You ever try to spell a word and both look wrong, but one of them is? I think it's got an E. It's pronounced parallelepiped anyway. And what in the heck is it? You have three vectors, A, B, and C. They start at the same point. You could make it the origin, but it doesn't matter. And can you imagine that vector A is going this way? That vector B is going this way. And let's have vector C going this way. So can you imagine leaving that point? This is not going to work, I don't think, but I'll try it anyway. And you've got three vectors leaving it, right? You see those three vectors? It's getting kind of messy, this. Now, if you use a little bit of imagination and you do another vector parallel to this fella and another vector going this way parallel to this vector and another one going this way and another one going this way and one going down this way and one going up that way. Do you see what I've basically built in 3D space? That's meant to represent 3D space. That's what they call a parallelepiped. I like to think of it as a three-dimensional version of a parallelogram. It's a bit like a shoebox that somebody sat on and kind of bent out of shape. Can you kind of visualize that in your head, what that shape might look like? Right, it's a solid shape where the three edges are formed by the vectors A, B, and C. And how do cross products come in here? Well, the volume of this shape is given by this, which means we're now going to take a dot product of the cross product of B and C. Now, this is one of the three versions. It might seem unlikely, but it's in fact true that it doesn't matter which one you decide to put here on its own, and it doesn't matter then who the two that are left that gets cross products. These three things are all numbers and they're all the same number, even although in this case you're doing the cross product of B and C, and then whatever that answer is, you're doing the dot product of A with it. In this case, we're switching the order. In this case, we're switching the order. Now, there's a little proviso at the end of this I'm going to say. Do you know that the B and C can be switched around? So you could do C cross B, C cross A, and B cross A. But there is a problem. If you take a vector B cross C, and then you find the vector C cross B, isn't this guy the negative of the other guy? Remember we talked about that on lecture 2, right? That when you reverse the order that you do the cross product, although you get a similar vector, you get the negative direction of it. Which means that we now have to stick this thing through it. So technically, it's the absolute value of this. Now, I'm using the word absolute value here, not magnitude. And the reason I'm doing that is, let's look at this one. Isn't B cross C just a vector? Isn't A dot a vector a number, what we call a scalar? So if you find the magnitude of a scalar, you're actually finding the absolute value of it. So that means the absolute value of -3 gets you 3. Well, that's the gist of this. So let's invent a question to go along with it. Suppose that's A. This is B. And this is C. So can you imagine these are the 3 vectors here? And the question is asking us to find the volume of the parallelepiped. For no particular reason except its alphabetical order, this is the calculation that will find that. Now, I guess, again, you're probably thinking, how does that work? Why is that true? And my answer is going to be, it is magic. Trust me, I'm a mathematician. It works. I know that's very unsatisfying. But if you do enough advanced math and you go into some of the more advanced linear algebra stuff, you may actually get to prove something similar to this. Right. Now, I haven't actually done the calculation yet. I'm going to do that in a few moments. But are we comfortable with the fact that 3 vectors typically generate this 3-dimensional parallelogram thing, which is called a parallelepiped, and that you can get its volume by doing any one of these 3 combinations? And we're about to do this fella. So what I would be looking at here is, let's find B cross C. So it's going to be the I vector, the j vector, and the k vector. B is 1, 1, -1, and C is 2, 3, -2. So we're going to get so many I, take away so many j's, plus so many k's. So it's kind of mechanical now, I hope. Major, -2, take away add 3, that gets me 1. -2 is the major, take away negative is add, so you get 0. And 3 take away 2 is 1, and that was a miracle, but I'm really kind of happy with that. You get 1, 0, 1. Now I do the dot product. So I'm going to do the vector 1, 2, 3, dot product with this fella. And that's 1 times 1, plus 2 times 0, plus 3 times 1. And that's 1, that's nothing, that's 3, and I get 4. Now, since that is a positive number, the volume is 4 cubic, whatever the units are. So if you did these 3 guys, and you created a kind of a wire framework using A, B, and C, and then that wire framework was extended with adding these extra sides here. Of course, there's some more down here. You would be able to say that the volume of this shape is 4. There is a name given to this calculation. This calculation is called a triple product. Now it uses cross products, it uses dot products, and there's 3 of them. So I think triple product's probably quite a good name for that particular calculation. Any questions about that? And it's very mechanical. To me, mechanical just means, you know, you put numbers in and you do whatever the process is, and out pops the answer, and that's the guy you're looking for. If this calculation had been -4, which I had 50-50 chance of being, all that would happen up here is that the volume would still be 4, because these 2 guys are saying the absolute value of whatever this number is. So if this number is negative, you choose a positive value. And that makes sense because volume is a physical thing. We talk about the volume of something as 4 cubic units. We don't typically say that the volume of something is -4 units. It doesn't have a very sensible meaning. Any questions? I think muting you all has had a bad effect. I think it's made you stop talking. I can imagine being a student here and have all sorts of kind of questions. For instance, I would be thinking at this and I'd be saying to myself, what happens if this calculation ends up being 0? And 0 is a very interesting answer, right? Dot products being 0 mean that the 2 vectors are orthogonal. Cross products being 0 means that the 2 vectors are in fact parallel. So triple product being 0 means that the volume of this object is nothing. So I'm going to put it over here. And I'm going to try and tell you what it means geometrically. Now you notice it's the number 0, not the vector 0, because this is a number. I don't need the absolute values around it because 0 is 0, right? It's not positive, it's not negative.
We're not looking over your paper. We're
Thank you. I'll zoom back in and show you. Here we go. Right. That guy that I said we were going to talk about, if the triple product is 0, it means that the 3 vectors A, B, and C are coplanar. What does that mean? Can you imagine a piece of paper in 3D space? So we're not talking horizontal, we're talking about like at an angle, right? If you take a piece of paper, let's use this one, and it's in 3D space, like this piece of paper here is, if all 3 vectors are on the same piece of paper, we say that the vectors A, B, and C are coplanar. So can you imagine you started at a point and you did A going this way, and you did B going this way, and you did C going this way? Those 3 vectors would be on this piece of paper. This piece of paper might be an angle, but they're on this piece of paper. And we say not collinear, that would be for 3 points on the same straight line. But we say collinear, that means 3 vectors in the same 2-dimensional plane. So they all lie in the single plane. That's kind of interesting property. Are we cool? No questions? Okay. I would be thinking, this is my brain again, I would be thinking, well, if this makes them coplanar, and we're assuming all the time I say this, that A, B, and C aren't the 0 vector, because the minute you make one of those 3 a 0 vector, everything ends up being 0 because of that. Then I should be able to get all sorts of combinations out of that. For instance, what would happen if A, B, and C were all parallel to each other? what do you think the triple product would be in that case?
Wouldn't they still have to be coplanar to be parallel to each other?
Yes. So it's just a very special case of coplanar. So the answer would be you would still get 0. You're right. So we're going to imagine these different kinds of combinations here, but most of them end up being, if it's a number, it means that the 3 vectors are not particularly interesting, they're just random vectors. But when that happens, you actually create one of these funny shapes called parallelepiped, which means the volume will be a number. But the other alternative is that this triple product is 0. And the combinations of it being 0 are the 3 vectors are coplanar. The 3 vectors could be parallel to each other, but that's just a special case of coplanar. You could have 2 parallel and 1 not. That would still be technically a coplanar situation as well. Okay, let's have a look at some of the homework questions. I think I got it set up here. Here it goes. Okay, so this is us looking at 12(4), the cross product. In question 1, it's a classic. Here are 2 vectors, find the cross product, and then check it out. When you find the cross product, let's pretend it's 1, 2, 3. Won't the guy that goes in here be 0 and the guy that goes in here be 0? Because what they are doing is they're just checking that A is perpendicular to the cross product, and this one is checking that B is. And there's another, essentially the same as question 1. Here is an example, nothing too special. Here they're talking about which ones have meaning, which ones don't. We remember talking about that last time. Here's some cross products. Let's touch on this again. Imagine this cross product here was 1, 2, 3. Wouldn't B cross A be -1, -2, -3? Good. Can you see over here a little thing called, they're calling the calc pad?
Yeah.
Right. See if I click on the vectors heading, do you see the I, J, and K that you need to use when you give your answer in that format? That's what I was talking about at the start of today. So if the vector has to be written as 2i plus 3j plus 4k, these are going to be the I, the j, and the k that you use. Oh, I didn't do this one. This is interesting. I think I will get this set up in a moment. Find the area of a parallelogram. It's a 2D question, at least it looks like it. So once I've left this, we'll come back to this question because I haven't looked at how you would deal with it. Okay. Okay, question 7. Here are 3 points called P, Q, and R. Find a non-zero vector orthogonal to the plane through the points P, Q, and R. Okay. That word orthogonal sticks out like a sore thumb. If you find the vector joining P and Q, and then you find the vector joining P and R, won't those 2 vectors be like your U and your V? So you find the cross product of P and Q with P and R, and that will be the answer to A. So you imagine 3 points, P, Q, and R. Actually, maybe you can't. Let's just jump back and then I'll do that other question while we're at it. Okay, imagine this is P, this is Q, down here is R. Right. If you find the vector PQ and PR, we'll call U the vector PQ, that's what I was saying. And V, I'm going to call that the vector PR. Won't the vector that's orthogonal to them, which is what question A was asking for, I'll call that vector W. Don't you get that by just finding U cross V? So do you see that was a disguised find the cross product where you had to do a little bit extra work. You had to find P, Q, and PR, and then you do the cross product of them. Now what, that was A. B was the area of the triangle. We're almost there. Haven't we found the cross product in part A? Then won't the area of the triangle be half the magnitude of the cross product? If they wanted to know what parallelogram was, then wouldn't it just be the magnitude of the cross product? But they want the triangle, so it's half that. Over here, we have an A. I'm calling that B. I'm calling that C. I'm calling that D. And I'm drawing a parallelogram because they told me it was a parallelogram. And we are going to find the area of this shape. Well, the first thing that strikes me is that these are two-dimensional points, so this is actually a flat piece of paper. Agreed? So, to do cross products, don't you need three-dimensional information, not two-dimensional information? So, what I'm going to do if I plotted these 4 points in 3 dimensions, wouldn't you still end up with that shape? In fact, wouldn't you end up with that shape on the floor, on the XY plane? So what I've done is artificially altered the information from two-dimensional, which I can't find cross products of two-dimensional anything, it doesn't really work, into three-dimensional. Now, I'm going to find AB, which is second takeaway first, so that takeaway that gets me 2, that takeaway that gets me 5, and that takeaway that gets me 0. And then I'm going to find AD, and 5 takeaway negative 3 is 8, negative 1 takeaway 0, and 0 takeaway 0. Now, coming to the point where I'm going to leave this question alone, if I want to find the area of this shape, isn't it the magnitude of this cross product? So you take these two guys together and you find their cross product. And then get the magnitude of that guy and you're finished. So that was the kind of the approach that I would have chosen to do that. As a strategy, does that make sense to you? Are you comfortable with how you could find the area of a parallelogram in two-dimensional space by converting it into a three-dimensional situation and using the magnitude of their cross products? Are we good? I get nods. Nods will do. Right, so let's just return back to the rest of what's going on here. There's question 8 is a parallelepiped. Oh, it does have an E in it. I was right. I wasn't sure whether that was an A or an E. It's an E. Parallelepiped. That's a cool word. When you talk to anybody and you say, what did you learn today? You can say, oh, we found out how to find the volume of a parallelepiped. Do you know that should be the name of an elf or something, shouldn't it? It's got a cool name. Okay, in question 9, find the volume of this PQRS guy. Now, I'm going to write that guy down, and we'll talk about the process of doing it. So P is going to be the 0.103. Q is going to be the -439. R is going to be the 0.311. And finally, S is going to be the -145. And we're being asked to find the volume of the parallelepiped. Okay. I don't need the specific numbers that you're going to use, but has anybody got a thought process about, so there's PEQ. Let's suppose R is over here, and let's suppose S is down there. So essentially, we have been given these 4 points. Now, to me, the minute I draw the thing, and I don't make any attempt to be accurate, it's just a placeholder, but it's good enough. Do you see where to go? Anybody got suggestions about how we would find the volume of this shape?
I think you would, so you would find the dot, no, you would find the dot product of PQ and PR, then you would find the dot product, the dot product of the cross product and PS.
Okay, I think I caught you. So we're going to go PQ and do those guys. If I call this fella A, and I call this guy B, and I call this guy C, what I've just written down here is A dot B cross C. Does that make sense? That really you're finding the triple product. But the vectors that I'm calling A, B, and C are really just the vectors that you get by joining 2 consecutive numbers. The only thing you have to make sure in this question is that you start at one of the numbers. I've decided alphabetically that P is going to be my central point, and all 3 vectors have to leave from P, right? So don't start mixing and matching, you know, different variations. Like, don't try and do a guy over here, or not that you would know how to do the guy, but don't have some guys pointing one way and then going QR and then going QS and so on. If you decide, whatever you decide, I would probably just pick the first letter. Make that your focal point and project the 3 vectors, A, B, and C, from that point. Now you find this fella, you get the magnitude of that, and now you've got the volume. So the information that you're given is the coordinates of the point, that they turn into vectors called A, B, and C, which generates a triple product, the magnitude of which is the volume that you're being asked to find. Okay. Now, they could have turned this question on its head and not even asked you to do that. They could have asked you this instead. In this particular question, it won't work, but imagine a different P, Q, R, and S. Prove that P, Q, R, and S are all coplanar, which means that all 4 points are on the same flat piece of paper. That's what coplanar would mean in this case. All the points, or all the vectors, it works in vector situations as well, they are all on the same flat piece of paper. Now, do you know that you would have approached it the same way we would have done this? The only difference is, what would this be equal to prove coplanar?
0.
That's it. So if the triple product generates 0 as an answer, it means that the 3 vectors, or the 4 coordinate points in this case, are all coplanar. So you see the triple product can be used to find volumes of parallelepipeds. It can also be used to prove things are coplanar. Or if it's not 0, you've just proved that they're not coplanar, right? They're just a usual kind of vector combination or point combination with nothing that special going on. And here is a good example of checking coplanar. They've got a vector u, a vector v, and a vector w. Now, in a question like this, the answer is clearly yes or no. If you get 0 as an answer, it's yes. If you get a number, it's no. But there's a fair amount of work in proving that, right? You have to find the cross product of v and w, and then you dot that to get the answer. Here's a thinking one, which I like thinking ones. Suppose A is not the 0 vector, and A dot B is equal to A dot C. Does that follow that B is equal to C? So you're 50-50 chance of guessing here, right? If A is not the 0 vector, but the dot product of A and B is the same number as the dot product of A and C, does it follow that B and C are equal to each other? The same vector. What do you think?
I think so.
I think
it's-
because it's a
Right.
vector, it doesn't have to be, because different coordinates can be different. And then when you add them together, they would add up to the same number, but they don't have to be equal.
Yeah, so we get two, as you'd expect, descending properties. The correct answer is no, they don't. You're right, they don't need to be equal to each other. You would think they should be. There's a kind of, can I not cancel the A on both sides and leave B equals C kind of algebra thing going on? Totally understandable why you would think that. But no, they don't need to be. In fact, let's imagine one. Could you imagine that B is perpendicular to A? So that would give you a dot product of 0, right? And maybe C is a 0 vector. Wouldn't that also give you a dot product of 0? That's just one example of it not happening. And that's the easiest one I can figure out in my head. Now, if A cross B is the same thing as A cross C, does it follow? Now, in a way, you're just maybe semi-guessing here, and that's fine. What do you think?
Well, now I want to say
Kind of
no.
is-
Now you want to say no.
I
Which
think
is-
it's kind of still the same thing as the dot product, because it's not necessarily a straight order of operations. So you can have different numbers in there, and then when you,
at the end of the day, you could end up with the same result, but from different routes.
yeah.
Yeah. Okay.
Though this one is all multiplication, so I could see how this.
Yeah, I think it's one of those things, isn't it, that both answers, once I tell you which it is, are acceptable. Yeah, I could imagine that happening. So let me look at it from a slightly different perspective here. Now, if you, I don't know why they keep bending at weird angles, but if you take this guy and you subtract that guy, you do get the 0 vector. That is acceptable. This is a vector, that is a vector. This vector, take away that vector, will be the 0, right? That is acceptable. You are allowed to pull out A as essentially a common factor, That is acceptable in cross products as well. It's also acceptable, by the way, in dot products, right? So far, so good. Now, what do you know if two things have a cross product of 0? What do you know about A and the vector B take away C? When their cross product is 0, you know something about the two vectors. Starts with a P.
They're parallel.
Yeah. Which means that the vector A is some multiple of B take away C. So far, so good. Right. Agreed? Now, if B and C were equal, what would B take away C be equal to?
0.
And you're saying that any vector A is going to be k times the 0 vector, which means you're saying A can only be the 0 vector. Do you see that's a contradiction?
Yeah.
So that means they're never going to be equal to each other. Except, I
Well,
guess, unless you get 0 vector, right?
They could, but yeah, if you get 0, then that's pretty obvious.
Right. So I'm not sure if that's a proof, but at least does it justify my argument that no, they shouldn't be equal to each other. It is kind of interesting that the rules of algebra that we are comfortable with, because we've been using them for so long, don't quite work when you do cross products. You know, A times B is B times A in good old fashioned Calc 1 world, right? AB is BA. We use that a lot. But isn't A cross B not B cross A in the vector cross product world? See, they're quite different. Right, question 12, cross products with dots, cross products, cross products. Cross product where some of the guys are now variables. I think I should do one of those. I'll make up my own. So essentially, you're going to find the cross product of two vectors. The difference is that the vectors themselves do not have anything, they don't have numbers in them, they have variables in them, t's or whatever. Right, so suppose, I'll do my own vector. Suppose A was t squared 1, and B was a vector 2 plus t, 3t, something like that. If you were being asked to find the cross product of those, go through the exact same mechanical process that you would do if everybody was a number. So t squared and 1. 2 plus t, 3, and t. And then you'd get so many i's, take away so many j's, plus so many k's. Then I'd cover this guy up, and it would be major diagonal t cubed, take away minor diagonal 3, major diagonal t squared, take away one of these. So you take away those two guys. And then 3t, take away that guy. Oh God, that's going to be messy. So what you get? You're going to get a negative t cubed, a negative 2t squared, and a 3t. So make it look pretty. T cubed take away 3. If you take the negative of that, everybody kind of switches signs, and then you've got that guy to finish. Nothing particularly nice about that, it's just what it is, and that would be your answer. I don't know if the two examples in the homework, maybe there's a lot more cancelling and combining than my example is, but the process will be the same. So that's what you're being asked to do in that particular situation. It's time for me to show you a new guy. Question 17. Yeah, the last two are just basic baby stuff. So the only thing I haven't covered is question 17. So I'm going to show you that one in a few moments from now. Actually, I think an easier way for me to do this would be to go up here and show you it that way. That way we could speed up some time. 17. Okay. I don't know, can you see this? Because sometimes when I go inside another level, things disappear. Are you looking at the solution to this?
No, we're not.
Okay, then that wasn't worth all the effort I just did. I will show you it the long way. Right, so the last question that we're having to deal with here is, if you're told this kind of position, I'm making up my own example of it, that you've got a vector u going, say, this way and a vector v going this way, and the angle between them is 30 degrees. So it's your classic, you know, these two pens sticking out of the board. That angle's 30 degrees. This guy's 4 units long. Let's say this guy here is 11 units long. The angle between them is 30 degrees. And you're being asked to find the magnitude of the cross product. Well, it's equal to the magnitude of u times the magnitude of v times the sine of theta. Can you, I think it was at the end of lesson 1, it might have been the end of lesson 2, I can't remember now, I think it was 1, where I was doing the dot product. And I was saying, look, the dot product is this guy here. Can you see how I got them mixed up in my poor brain? Aren't they very, very, very similar to each other? And that is amazing that this relationship is even so close. The dot product, which is a number, is the magnitude of u times the magnitude of v times cosine theta. We don't typically use it that way, but we can, because if you rearrange that, doesn't it give you a formula for calculating the angle by finding cosine theta? Well, here we have another relationship. It says that the magnitude of the cross product, so that means it's a number, is the length of vector u, the magnitude of v, and the sine of angle in between. So in this case here, if you want to calculate that guy, it's 4 times 11 times the sine of 30 degrees.
Okay.
What else is the magnitude of u cross v? Geometrically, what does the magnitude of u cross v get you?
The area, or yeah, the area.
Yes. So if someone went and said to you, I would like you to find the area of the parallelogram generated by two vectors u and v that are of these lengths. Well, thank you. U and v, and the angle between them is 30 degrees. Then I could simply just use this formula, couldn't I? And I would get the area of that parallelogram really quite quickly.
Mr. Robertson,
Yes.
why is it sine theta when you calculate the magnitude of the cross product? Why is sine theta in there?
I think I'm going to have a small recording of myself when I say this. It's not going to be a nice answer. Trust me, I'm a mathematician. It works. That's all I'm going to tell you. I mean, if you really wanted to find out, because a lot of people they don't like magic. I don't like magic myself. You can certainly go online and basically just do a search of the proof of the dot product or the proof of the cross product. And there'll be someone who's given a nice little whatever it would be, 10-minute lecture on it, and you can actually find out that way. I don't want to get caught up too much in the weeds, because if we went through the process of proving it to you, it would probably take me longer than 10 minutes to do that. And at the end of the day, the only benefit you would be getting is that that's the formula that you use and it works. So we just don't tell you, which is unsatisfying. But then you've got things to look forward to, don't you have in the future? You're going to eventually, hopefully some of you anyway. Oh, I remember 4 years ago or 3 years ago, we were just told that that was true. And now I see the proof of why it is true. Everything that you do in mathematics is provable. We just don't necessarily prove it to you when you use it. Well, that's us finished that section. So we're now going to move on to lines and planes. In 3 dimensions. In particular, their equations. Right, let's start with lines. In 3 dimensions. Imagine this pen. This is a line in 3D. Can you imagine the pen continuing to eternity? How do we generate an equation that will allow us to tell all the points in 3D space that lie in that line? Because that's essentially what an equation does, right? It says, you know, when I do it in 2D, y equals 2x, for instance. Isn't that the equation of a line in 2 dimensions? Well, at least if I tell you it's 2 dimensions, it is, right? But if I plug in an x, won't the y be twice the x, and that's the relationship? That's how you would do it in 2D world. In the 3D world, it's much more difficult because, can you imagine this is representing my pen? If you choose points on this line, and it continues forever, they have an x, a y, and a z component. So we have to come up with a way of generating an equation that allows us to find the coordinates of every point on this 3D line. So how do they do it? Well, you know, in the 2D world, if I tell you the coordinates of one point, and I tell you the slope, isn't that enough information for you to get the equation of a line? You agree if I tell you the slope of a line and just one point on that line, can't you generate the equation of that line? Agreed?
Yes.
Right. So how are we going to do that same thing? Well, in the 3D world, find one point on the line. Let's call it that guy. Now, we have a bit of a problem with slope. You don't have slope in 3D world. What you have instead is a vector called the direction vector. So let's just pretend that this direction vector was 1, 2, 3. So if you start at the point P and you want to draw the line, can you imagine from P, you just draw the vector 1, 2, 3, and then you say, look, imagine that vector just continuing, you know, like a space rocket, right, forever. Wouldn't that generate a straight line? Agreed?
Yes.
Right. So how does this, what does it look like? Well, when you do the equation of a straight line, you use 2 different types of equation. One's called the parametric equation, which is the one I'm going to show you right now. And the second one is called the symmetric. Nope, 1 min. Symmetric equation. Right. Okay, let's suppose then I have a point on the line and its coordinates are 1, 4, -3, and I have a direction vector 1, 2, and 3. Then you can imagine this is the point P, and this is the direction vector V. If you want to find any point on this line, any point at all, what you would have is this guy, and it's converted into what's called a position vector. A position vector is, imagine the origins down here. You got the position vector of the point P, which is just basically the same numbers as its coordinates, because if you join a vector to the origin, won't the coordinates of the point be the same numbers as the components of its vector? Right. Now, you choose a random point. So this is me actually going to prove to you the parametric equation of a line. So we'll have this guy here, and we'll call him Q. Right. So can you imagine the vector joining that guy? And we will call this vector Q. And Q is going to be X, Y, and Z, because Q is going to represent any point on this line. So far, so good. So I have got a starting point which is fixed. This point here has coordinates 1, 4, -3, and it's got a position vector. I got a vector V, which is this fella here. And now we're going to look at how these two are related to each other. Well, if I wanted to get this vector here, can you imagine it could be made up of going from O to P and then going from P to Q? That's the same thing as OQ. That's the same thing as X, Y, Z. OP is 1, 4, -3. And now we just have to figure out how to represent PQ. Well, isn't PQ parallel to V, which means it's a multiple of V. So let's call it TV. So it's going to be T times the vector V. And so OQ is 1, 4, -3 plus T, 2T, and 3T. And I'll turn it back into X, Y, Z again. And what do you get? You get 1 plus T, 4 plus 2T, and -3 plus 3T. So that is the equation of this line. You write it down like this. That's its parametric form. You will find that they very often write it down this way. It's also called its parametric form. Now, the good news is you do not build equations of straight lines in 3D space by going through all of this process. There is a formula for it. And it's a formula that normally I would just say it is magic, trust me. But this one is relatively easy to prove the long way, which is what I've basically done. So now I'm going to give you the magic of how you can find the equation of any line in 3D space. So here we go. The equation of a line that passes through the point P, we'll call the point P ABC, with a direction vector. So we're going to have to call the direction vector something else. So what do I want to call it? ABC, PQR. Actually, let me change. Let me call this ABC. And let me call this X naught, Y naught, Z naught. That's probably a better notation. Then you want the equation? It's start again, because of my changing. It's X naught plus AT. It's Y naught plus BT. And it's Z naught plus CT. So if you make P call X naught, Y naught, Z naught, and you make the direction vector, let's call it ABC, then here is your equation of that straight line. Okay, let's put one into practice. Suppose P was 1, -1, 5. Suppose the direction of the vector that represents the direction of that line was 1, 3, -2. Then the equation of this line would be as follows. 1 plus 1t. -1 plus 3t. 5 minus 2t. Or, in its more compact version, 1t minus 1 plus 3t, 5 take away 2t. So it's actually relatively straightforward once you realize that the whole thing is really just equivalent in a lot of ways to finding the equation of a line in 2D. This is like the replacement for the slope, and this is the given point. So if you're told the point on the line and you're told the direction vector, this represents all the points in that line. So you might say, well, how does it work? How do I actually find points on the line? Well, do you want to find the point on the line when t is 0? You get 1 plus 0 is 1, -1 plus 0 is -1, 5 take away, you get 5. This is a vector, but it's called a position vector, which means it's the same thing as the vector joining the origin to that point. So it tells me that the point on the line has coordinates. You see the connection, it's the same numbers. Now, what about when t is 1? Well, you get 1 plus 1 is 2, -1 plus 3 is 2, 5 take away 2 is 3. So at this particular place, you get another guy, I guess I'll call him Q. And with that guy, oops, curve bracket. So for any given value of t, can you imagine plugging in different values of t? The answer that you get converts into a point, and that's a point on the line. So the thing that we call a position vector is the same thing as the coordinates. The position vector is just the vector you get by joining the point to the origin. So that's why the numbers match. Are we go? Now, you will see different versions of how this formula is written. That's the same formula. The position vector of P would be this guy. V would be this guy. And that T is just a scalar value, T times vector. So you put that together and you will generate this vector up here. I'm going to have a look at some faces here because I do not know whether that is sensible or weird, or I don't know what you're talking about. Okay, so your chance to tell me is, we got any issues about the creating of the equation of a line in 3D space? In particular, are you comfortable with the formula that we use? I'm looking at some faces, but not many. James, you're smiling. Is that a good smile or a not so good smile?
It's good.
Okay, good. So I'm not going to be too worried then. Okay, so, oh, we got a thumbs up. That I like thumbs up. Okay, it's sometimes I would. I guess it depends on where you've came from, you know, what your previous math has been like. So I'm going to do some questions on calculating the parametric equation of a line in 3D. Oh, I had a little side note. Do you know the equations that we've been dealing with? These guys here. Oh, if you can see the bottom, I'm never sure about this thing. T is very often not just a variable they use because they like the letter T. Do you know T very often represents time? So what you're really doing is you're not just modeling all the points on a straight line. You're actually modeling where it would be at the 1 second mark, at the 2 second mark, and at the 3 second mark. And the initial point, right, the starting point, the one I'm calling P, is where the object is at time 0. And if you use negative numbers, what you're basically doing is following the line backwards into the past. So it's another interesting thing. So suppose I give you the point with coordinates 1, 3, 5, and another point Q, 5, 7, negative 2. And the question was, find the equation of the line passing through these 2 points. Do you know that? I mean, if I took these 2 numbers off, wouldn't that be a Math 94 question? Find the equation of a line passing through 2 points. Now, in 3D space, if you want a line, you only need 2 points, right? I need to know the tip and the bottom and the top of that pen. That's enough to generate a line forever. Well, I need 2 pieces of information. I need to know a point on the line. And the second piece of information I need to get is the direction vector. Well, the point on the line's pretty easy. 1, 3, 5. And I'm going to call that x naught, y naught, z naught. And, how am I going to get the direction vector? How am I going to get the direction vector?
Just make a vector out of point P,
And
Q. Yeah, make a vector out of PQ.
and we're good. So in this case, 5 take away 1 gets you 4. 7 take away 3 gets you 4. Negative 2 take away 5 gets you negative 7. Right, you put those together. Let's do the shortened version, which is the one where you put it all together like this. So where are you going to go? You're going to get this guy, 1, plus 4t. You're going to get this guy, 3, plus 4t. And then you're going to get this guy, 5, minus 7t. Do you see how clean it is? P plus a multiple of the t times the direction vector, the y coordinate, t times its position vector, and the z coordinate. Again, are we cool? Are we good, guys? Right, so I don't think you would do that in the in the physics class, in the kinematics class. Did you ever find it? Right, so this is kind of new stuff. So in a way, that's kind of good, right? Something you haven't seen before. Now, I said that there were two different equations for a straight line. This one in all its various flavors, right? This is called the parametric equation, or the parametric form, if you want to use that word. That's the guys we've just done here. Now, there is a second one, which is called the symmetric form. Now, let's do it as a general version. I'm not going to prove this one. Let's suppose we have a point, P0, Y0, Z0, and let's have a direction vector. I'm going to call it A, B, and C to be consistent. You're going to trust me on this one. It's a lot messier to prove, but X take away X0 over A is equal to Y take away Y0 over B equals Z take away Z0 over C. That is called the symmetric form of the equation of a line in 3D. So it's the symmetric form of the equation of a line in 3D. So if I told you that P was 1, -1, 2, and that the direction vector was 3, -2, 5, for example, then this would be X take away 1 over 3 is equal to Y plus 1 over -2 equals Z subtract 2 over 5. And that would be the symmetric form for the equation of a line. Me in particular, and probably quite a lot of people would agree with me, much prefer parametric equation, because in this format it's relatively easy, isn't it, to calculate the coordinates of various points that lie in that line. Don't you just plug in 0, t is 2, t equals 57 because I felt like it, and every single value of t would tell me 1 point on that line. And you know, if I put enough of them together, I get an idea. When it's written down in this format, do you see how much more difficult it is to generate points that lie on the line? Right? Suppose I wanted to know a point that lies on this line. What I would have to do is I'd have to say, well, I'll just randomly pick an x value, 4. Now, if you plug 4 in here, and I did choose it for a good reason, 4 take away 1 is 3. 3 over 3 equals 1. That makes this equal to 1. So what you need to do now is pick a y value to make this equal 1, and you have to pick a z value to make this equals 1. So whatever this equals, right, whatever this fraction equals, the other two have to equal that same fraction. So in this case, I made it 1. So if I wanted this to be equal to 1, then y plus 1 would have to equal -2. So that would make y would have to be -3 then. If I wanted this to be 1, wouldn't z minus 2 have to be 5, which would make what? Z equals 7. And that would be a point on this line. Do you see how much more clunky it is? It has some advantages. For instance, if you knew that the x coordinate was 4, wouldn't you be able to use this technique to find out what the y and z coordinate of that point were? In the kind of 2D world where here's the equation of a line, the x coordinate is 7, right? Tell me what the y coordinate would be. Here it would be the x coordinate is 4, tell me what the y and z coordinates. So it has that advantage. If I did the same kind of question over here and I said to you, the x coordinate was 9, tell me what the y and z coordinates would be. That wouldn't be so clean. If I told you that the x coordinate was 9, find the corresponding y and z coordinates, wouldn't you first have to go up here and say, okay, if the x coordinate is 9, you've indirectly told me the t value. And now I know the t value. Can't I figure out that y is 3 plus 8 and z is 5 take away 14, and there's the y and z that match it. It's a little bit different. Agreed? Now, let's talk about special cases of straight lines. Right? So, suppose I have a point P, 1, 2, 3. And the direction vector is 1, 2, 0. Then the parametric equation of this line is 1 plus 1t, 2 plus 2t, and 3, okay, 3 plus what?
Wouldn't it just be,
Yeah, finish that sentence. Wouldn't it just be?
wouldn't it just be 3 because it's 3 plus 0 times t?
Yeah. So no big headache. Would you agree in this equation here in parametric form, all 3 of them or 2 of them could be zeros, and it really isn't too hard to cope with, right? Same story. I'm now about to try and do the same equation of this line, but I'm going to now use its symmetric form and watch the problem, because it's a kind of awkwardness. X take away 1 divided by 1. Y take away 2 divided by 2. Okay. Z take away 3 divided by O. That's not good. Would you agree that is not good? You can't have things divided by 0. We've learned well into our math life that dividing by 0 is a very bad idea. So how does this get written down in symmetric form? It is not written the way I've just written it. It's not written that way. This one is only cosmetic, but typically you just write that, because sum over 1 is 1. You make it equal to this guy, and then you do comma, z equals 3. So this would be the correct version of the equation of this particular line in symmetric form. Okay. So that's how you cope with the zeros. Vectors don't care about zeros. Aren't zeros really easy to take care of? Couldn't I have any one of those 3 being 0, and its vector equation would be trivial. You'd be able to figure it out without any issues. So far, so good? Now, here's a problem, and it's a weird one. How do you convert from the parametric equation of a line to the symmetric equation of a line, and vice versa? So let's give you the equation of a line.
To convert from parametric to symmetric, you want to like solve for t. What does t equal with respect to x, y, or z? If you want to convert to symmetric and from symmetric to parametric, you want to put t on the other side of the equation so that you see what x equals, what y equals, and what z equals.
Nailed it. Bang on. Exactly what you just said. Bang on. So let me take you through what you just said. Right. You know this makes x, and this makes y, and this makes z. Right? So if you wrote it down in kind of its full format, it would look something like this, right? Now, if you subtract 1 from both sides and divide by 2, we've got t. Now, if you take the second one, that's what y is equal to. You get that. And if you take the z coordinate, just this fella, you get that. Now, these are all equal to each other because they're all equal to t. And now we've converted it. That makes sense? Right, let's go the other way. Suppose you had x plus 1 over 5 is y plus 2 over negative 2 is z minus 1 over 3. Right, now that is symmetric form, but I would like to know what does that look like if we convert it into parametric form? Well, you just make it equal to t. And then you take each one and kind of undo this process. So if you took just this guy equals t, for example, x plus 1 over 5, call it t, then won't x plus 1 be 5t? And won't that make x, I guess I should write the number first, negative 1 plus 5t. Do you see you've already got one of the three components, x. Then you do it with y, and then you do it with z. Agreed? Now, if you've got a really good memory, you can do it really quickly. Can you see where the numbers go in a symmetric and where the same numbers go in a parametric? So if you see enough of one equation, you should be able to transfer it into the other. So let's see if I can do this. Right, that is a symmetric equation of a line. Let's see if I can write down its parametric equation without doing a whole load of algebra every single time, just by using location and pattern. Right, there's a negative 3 here, there's a 2 in the bottom. It's all about what numbers get used. Doesn't the negative 3 become positive 3 and the 2 gets you 2t? Right, y plus 1 on the top, 5 on the bottom. Doesn't that get you negative 1 plus 5t? Last one, z minus 1 on the top, so minus 1 on the top, negative 4 on the bottom. What does the negative 1 get you? Gets you a 1. What does the negative 4 get you? It gets you negative 4t. Do you see how I could do that conversion in my head? I mean, this is the reason why it works. But if you do it enough times, you can short circuit the whole process and just do it by number and location, right? What's the number and where is it? Because you notice when it's a number on the top, it's a negative of it, and the number on the bottom is a multiple of t. Now you can switch that. Okay, here is a parametric equation of a line. Let's see if we can do that guy in its symmetric form. Okay, the first one, x, right? The numbers we're going to get are coming from here, right? What number goes on the bottom?
2.
2.
Yeah, not t, just 2, yeah. What number goes in the top, 5 or negative 5?
Negative 5.
Move on to the second one. Would you agree the number that goes in the bottom is the multiple of t, negative 5? And what goes in the top, y plus 3 or y take away 3?
Y minus 3.
And then if you go to the z guy, do you see 1t means 1? And z take away 1. Parametric to symmetric, right? I should say symmetric to parametric and parametric to symmetric. Any questions about that? So let's do a recap. If I give you 2 points in 3-dimensional space, and I ask you to find the equation of that line, are you comfortable about the process? How you would do it? And it doesn't matter if I say give the equation of the line in parametric form or give the equation of the line in symmetric form. You know, so essentially it's going to be the same process, although you're probably going to find the parametric first because that's the easier version. And then if you need to, convert the parametric to this. So that's typically my order. Get this guy first. And if you have to, because you don't always have to, convert it after the amount. If I gave you the equation of a line like this, it wouldn't be too difficult to find points on that line. Wouldn't you just click t is 0, t equals 1, t equals 22, and you get lots of possibles. If I gave you it in this form, could you find points that are on that line? Feel comfortable about that, right? So here's the next thing we're going to look at. I'm going to look at the equation of a line in parametric form first. So let's suppose we're told it. And I ask you this question. Does this particular point, I'll call it Q, with coordinates -3, 5, and 8, does it lie on this line? So you imagine this is a 3-dimensional line, right, traveling forever. If you plotted the point -3, 5, 8, would it be floating out here or would it be on the line? So your choices are going to be yes, no. So it's not going to be a hard thing to answer physically. You just say yes it is or no it's not. But we have to figure out which of those two it is. So we need a strategy. What would be a way of tackling this problem? I'm sure there are a couple of ways, but what would be most likely way you think you should tackle it?
Well, because basically the only thing you can change is t. So I would the x coordinate in your vector to the equal to the first point and find out what t equals.
Okay.
And then
so in this case, if I jump ahead of your thought process, t is 2, right?
Yes. And then if you plug that into t for every point and it equals that point, it should lie on there.
Okay, so if I plug it into here, 2, then the y coordinate should be 1 plus 2t. It should be 1 plus 2 lots of 2, which is 5. And if I plug in here, the z should be 2 plus 3t, which is 2 plus 3 lots of 2, which equals 8. And I guess the question is, did that in fact work? And the answer is yes in this case. Now imagine it was the same question, but that wasn't 5, that was say 15. Well, it could be. In which case it would fail, right? And I wouldn't even bother checking the third one because it doesn't matter, right? If the y coordinates don't match, it's never going to work. That make sense? So the question would be, does this point lie on the line with a given vector equation or a parametric equation in this case? How about the other similar idea? Suppose we get this fella and I ask you, does the point 7, 1, 2, does that lie on the line? The answer is going to be yes or no. How do you think we're going to tackle this one? I think you're talking, James, but I can't hear you. So if
I was gonna say convert it and then solve the same way.
Oh, that's a sneaky way of doing it. That's a cool way. If I'm picking you up, right, don't you just pretend that's T and you turn into this guy and you solve it, right? Yeah, nothing wrong with it. Suppose I didn't want to do that just because I don't, right? I had a bad night and I just don't want to do that. Give me another approach. Nothing wrong with that. Do it. It works. You're fine. Not criticizing. It's a good method. But give me another method. Kenton, you got an idea?
Yeah, I'd say just plug your X, Y, and Z in and see if they equal each other.
Oh, okay. So if I'm picking you right, oops. Start with that guy and plug in 7. Then plug it in here. What case? 1. Oh, stop looking, right? If they're not all the same, if they're not in this case all 3, right? Then so your answer will be no. Does that seem like a reasonable approach? I mean, the convert it into parametric and do the same approach here is totally valid. But I'm just saying it's a slightly different approach to the same situation. Can you imagine a question that went something like this? And this is not a very efficient way of proving it, but I guess they could do it this way just to get you to do things. That they give you 3 points. And they ask you, are they collinear? In other words, they're all in the same straight line. Now, we have lots of ways of doing that right now. Couldn't we find PQ and PR and see if they're multiples of each other? Couldn't we find PQ and PR and prove that the cross product was 0? Nice. But let's do it with equations. I'm not going to do the whole thing. It'd be too time consuming. But if I just use the points P and Q, can you imagine I should be able to get the equation of a line joining P to Q? So the first thing I would do is, because maybe they asked me, find the equation.
I hate to
Also-
interrupt, Professor, but it's 9:30.
No, it's not. I got 1 minute left. I'm going for it. Right. So you find it. I'll finish off. You're quite right. I should finish off right now. But here we go. Find the equation of the line joining P to Q. And then the second thing is test is R on the same line. Would you agree that'd be a long-winded way of proving it? But that would be collinear, wouldn't it? You know, P and Q are definitely going to be in the straight line because 2 points, unless they're identical, are going to generate a line. And then you just find out if R is on that line by the way that we just checked it before. And I think that is a good time for us to finish.